Hi, my name's Andrew Dawson, and I'm Senior Applications Engineer at Dynamic Signals, makers of high-performance GaGe instruments for the PC. Today I'm going to show you how to construct a portable, easy-to-use digitizer solution for remote and distributed testing. Imagine that you were charged with setting up a system to monitor multiple high-speed signals. Assume also that that system had to be accessible, controllable, and operable by multiple users. Now, you could set up such a system on your own. You could buy multiple GaGe boards, install them in PCs at the appropriate locations, connect them to a LAN. You could write the glue software that allowed you to control these multiple systems. But doesn't that sound like a lot of work? We've done this for you in the new GaGe FCI-X. This is an 8-channel GaGe FCI-X unit. As you can see, FCI stands for Faceless Connected Instrument. By instrument, we mean that the unit is a high-performance standalone oscilloscope. But unlike a conventional oscilloscope, it's faceless. By faceless, we mean that it doesn't have a built-in display, nor does it have any controlling knobs. Instead, the unit is connected through a standard Ethernet cable out the back. The cable is the means by which the unit is controlled and through which data is passed to the host PC that then displays the data. Out the front, we have the 8 input connectors to the oscilloscope. That provides 8 simultaneous inputs at up to 125 megasamples per second, 14 bits of vertical resolution, and a full gigasample of internal acquisition memory. This diagram shows the power of the FCI-X's network connectivity. We have, first of all, a LAN network, a local area network running throughout the facility, and on the top right we see a GaGe FCI-X connected to the LAN. Next we have 2 users connected directly to the LAN, presumably from their offices. On the lower right we have a user remotely connected to the LAN, presumably from home, and then on the left we have a user connected through a wireless router to the LAN from his smartphone. All of these users can control the FCI-X and monitor data coming from it. In order to demonstrate the power of the FCI-X, we've set up this simple ultrasonic demo. So what we have here is a standard fish aquarium equipped with a 5 megahertz ultrasonic transducer positioned at the bottom of the aquarium. The transducer is excited by an ultrasonic pulsar receiver which creates the high voltage necessary for the transducer and outputs a simple plus or minus 1 volt signal suitable for the FCI-X. So at a rate of several thousand times per second, an ultrasonic pulse is emitted by the transducer which travels up towards the surface of the water, which acts like a mirror and reflects the ultrasound back towards the ultrasonic transducer. So as long as everything's still the way we show it now, we expect to see a nice healthy ultrasonic echo. But as soon as we agitate the surface of the water, perhaps by this little toy submarine, we would expect the ripples on the surface to displace the echo such that it doesn't go back into the transducer. And we'll expect to see the echo of lower amplitude and perhaps shifted in time a bit. We'll see this now on GageScope when looking at the data coming from the FCI-X. This is the host laptop computer from which I'm controlling the FCI-X unit through this Ethernet cable. Now, the actual FCI-X unit is only a few feet away, but I could equally well be several offices away, or if I was using a remote desktop connection, I could be several time zones away. I'm controlling the FCI-X unit from GageScope, which is GaGe's very powerful oscilloscope software, but I could equally well be controlling it from a software development kit program written in C, LabVIEW, MATLAB, or a host of other programming languages. Here we see GageScope capturing 4 signals from the FCI-X. As you can see, channels 2 through 4 are capturing simple sine and square waves, But we're interested more in the ultrasonic signal on channel 1, so I'll zoom in on that. Now, if you recall, this echo is received by the transducer after the sound bounces off the ultrasonic mirror formed by the surface of the water. And because the aquarium is currently still, this echo is very stable in position and amplitude. But there, do you see that? The submarine just moved, and that caused ripples on the surface of the water, destroying the perfection, the idealness of the ultrasonic mirror. So the echo moves all around in position and amplitude. As time goes on, however, the tank eventually settles back and the surface becomes still, and the echo indeed returns to its former stable position and amplitude. I'd like to show you one more thing. From any web-enabled device, such as my wireless tablet or a smartphone, I can actually control and get data from an FCI-X. All I have to do is enter the web address into the browser, and as you can see, the live ultrasonic echo that we were looking at before comes up on the screen. For more information on GaGe FCI-X's or any other GaGe product, please visit our website at gage-applied.com.